This is lecture number 10 for chapter 5 of Calculus 3, and in this lecture I'll discuss surface integrals. So if we're looking to calculate flux across a surface, we're again looking at the tangential component of the vector field. In the past it was only the normal component of the vector field. In the past it was only the normal to a path, a one-dimensional object. In this case it will be over a surface. And the enclosed region would then be a volume. So we have a different way of finding the normal. So here's a summary of the steps, and you can read more about it in the book, but I hope what I've attempted to do in these lectures is to get down to the very essence. Mathematics isn't difficult. There's usually only a few basic core ideas. Once you have these core ideas, everything else is just an example, and you don't need a lot. So I hope I've gotten to the core idea, and one way to get to the core idea is to try to really simplify your notation, and I've made an effort to do that too. So it may not agree exactly with what you see in the text, but it's probably just a notation difference. So what we have here is we have flux on a 3D surface, a space across a surface. So the surface is in two dimensions. It's enclosing a volume. To parameterize this, we need two vectors. So here is an example of a vector field on two parameters. Okay, parameterization of a surface requires two parameters. I'm calling them u and v. And then this is going to create a three-dimensional surface in space. A two-dimensional surface in 3 space. All right, let's try to do this right. How confusing can you be? So I need two parameters. In the past, all we needed was r of t, and we got out a path, something that's one-dimensional. Here, we're going to get out something that's in 3 space, but actually it's only 2-dimensional. The reason it has 3 components is because it might be curved. For example, it might be a sphere. But we have these u and v are the parameters, and they take the place of the t that we had before. Again, it's a vector function, vectors coming from the origin up to the surface and defining the surface. We're going to need the first derivative. Remember, for 1D, for the path, we were looking for r dot, just the first derivative. Here, we have these two parameters, so our first derivatives will be partials. Ooh, that's supposed to be a partial right there. Okay, so you take the partial with respect to u and the partial with respect to v. Now we have these two. What is the normal? These are two vectors that are lying in that plane tangential to the surface of that point, or lying in the plane of the surface of that point, tangential if it's not a flat surface. The normal is a cross product of them. So this will be our normal. It's the outward, it would be the unit normal if we divide by the magnitude. So we're going to take the cross product of these derivatives to find the normal. This next step is exactly the same as the step for line integrals. You take the vector field and you compose it with the parameterization. Then, to get flux, we're going to project it onto the unit normal. So here's what the integral looks like. First we compose f with r. Remembering that r in this case is a function of two variables, u and v. We dot it with the normal. We know how to find the normal from the previous page. And then it's multiplied by the magnitude of the cross product of the vectors. Then you have to integrate over two variables, du and dv. Before we only integrated over dt. So you see how this is an extension? Because this was a path, a one-dimensional curve in 3 space. I probably shouldn't have that little circle in it, but okay. And here it's going to be over a surface. And that's why you have these two vectors. Here you are integrating only over dt. So if we go through here, making our substitutions, f composed with r dot in. Alright, so dot with the normal. So now we know what the normal is from previously. We have the cross product of these two. the magnitudes fall off, and this is what we get for the integral of a vector field, the normal component of the vector field. So we're looking at the normal component, so we're calculating flux through a surface, and the surface is defined by the parameterization UV. This is a vector. Sometimes the surface isn't described by that parameterization. Instead, it is a scalar field. Okay, we've seen those in the conic sections. All right. In this case, the normal is the gradient of f divided by its magnitude. You can see this is similar to what to the other. Okay, that's just another method for calculating the normal, and you'll see that discussed in length in Stewart. So let's do this example. We're going to have a solid ball. Remember, a ball is something that's solid. Could be a sphere that's filled up, whereas a sphere is usually taken to be a hollow sphere. The sphere is usually only the outside edge of the ball. At any rate, we have x squared plus y squared plus z squared is less than or equal to a, so we have a solid ball of radius a. And let's let this be our vector field, which looks similar or reminiscent of the conservative vector fields for the force, the electric force between two charged particles, or the gravitational force between two masses. Okay, without the constants given. Right, the boundary of the ball, which is where we're going to calculate this flux, is this surface, so it's equal to a. That's a sphere of radius a. And we can actually parameterize this in terms of two variables, phi and theta. I should have written theta second, but that's fine. Okay, and this will just describe that surface, a sphere of radius a, about the origin in 3 space. Now, if you remember, we wanted paths that were simple, could be traversed only once, and had a positive orientation. This boundary has similar qualities. First, it's a simple surface because it doesn't cross back and fold back on itself. The parameterization, the way we've written it, traverses the boundary only once. You can have a positive orientation to this curve. In other words, this curve, this surface, because you can have outward normals, a unique normal assigned at every point, and it can be a positive orientation because those normals will be pointing out of the sphere. So here are the derivatives of that parameterization. Remember, we needed those. They're right here. Then we're going to take that cross product to form the normal. And after getting rid of sine squared plus cosine squared, setting that equal to 1, we end up with this expression. So this is the normal from the sphere. Now look what happens. Every time theta and phi change, that normal changes, but you expect that because if you have a sphere, the normal out of it is pointing in different directions all over the sphere. Now we compose the vector field with the parameterization and simplify it a little bit, and this is what we get. Sine phi cosine theta in the I, sine phi sine theta in the j, and cosine phi in the k, all divided by a squared. That is the vector field on that surface. We need to take the dot product of that with the normal. You see, this is all just cookbook, and now you get an example. This gives you your integrand. And here's the integral of the flux across that sphere. Note the results independent of the radius of the sphere, which is interesting. And the answer is 4 pi. And when you study electromagnetics, that you might have studied already, you'll come into Gauss's law and you'll see this 4 pi again. There'll be some sign differences, but and some constants. But that's okay. Now you see how they got this. They had the equation. You take the parameterization for the sphere of any radius, a, we just used a. You follow this cookbook formula to find the derivative, to find the normal off of that surface. You take your vector field, f, and you compose it with that parameterization. Remember, it's going to be in 2 variables. You take the dot product of those two. That gives you the flux, that gives you the field that's pointing out, that's crossing the sphere, pointing out of the inside the volume of the sphere. And it's all in terms of the parameters, in this case theta and phi, and you just integrate them. And there you go, and you get your answer, and this 4 pi is a famous answer.